Welcome to the week 5 of problem solving session. Okay, so um, so today we will mostly look into linked lists and binary search trees. Or BSTs. Okay. Okay, so how did we define this data structure linked list? I think some of you might have already seen this, but yeah. So this is an abstract data structure where each node consists of some information. Here it could be integers or some information that you want. Additionally, it contains a pointer which points to the location of some other node. Okay, so again for the next cell there is some data which points and there's a pointer which points to the other node, and so on. And the last node here will point to null. Okay, so and how do you access this? If you have access to the first node, then you can follow these pointers and access any node in the list. So you need a pointer to the first cell, that's all. So yeah, so this is the data structure you saw in class, and if you want to insert um, yeah if you want to insert an element, then it's an order one operation. um, Insert n, this is an order one operation, because what you would do is you would create this new node, make it your head pointer, and point it to the start of the original linked list. So let's say this was the start of the list, then you point it here and don't really change anything, right? This one updation is all that we needed. But if you want to search for an element, um, then that's not easy, because that element could lie anywhere, potentially lie anywhere in this list, and you don't know where it is. So in the worst case you would end up using order and time. Okay. uh, okay, so that's your data structure. And okay. mm, yeah, so uh, one advantage it gives over arrays, for example, is that you don't commit to the space at the start. You can as in when you want your data structure to expand, you can just keep creating new nodes and insert them conveniently. So you don't need to, if you exhaust the size of the array, you don't really need to make larger and larger arrays as such. Okay, so okay. Okay, so consider the following question. um, let us say you are given two linked lists, L1 and L2. Okay, and what you want to do is you want to um, detect if there is, okay, let's not do detect, let's say find um, an intersection. Okay, so I'm talking about find. The detection is something I'll talk about later. So assume that given L1 and L2, there is definitely an intersection that happens. With that guarantee given, all you have to do is find where that intersection is. So let's say L1 looks like this. Mm. Um, okay, and L2 looks like this. Okay, so this is the position where they intersect, and you want to, so given L1 and L2 as inputs, all you have to do is output this position where the intersection happened. Okay. um, okay. Okay, so
So
okay, there was
what is
one
the
comment
question?
here that I'm seeing only now, so let me address that. So, no, it's not necessary that the insertion should happen at the start. Um, if you want, you can insert it anywhere you want. So you could, what you could do is maybe go 3 steps ahead, and maybe I want to insert, this is where I want to insert, then I will update this pointer to point to the new node, and wherever it was pointing, the I mean there was something somewhere, the place where it was pointing earlier, I will make the new node point there and let the rest of the list continue as it is. So you can insert wherever you want, but if you want fast insertions, then uh, ideally you would want to insert um, as early as possible. Okay. So,
So in this intersection, what what is the question here?
okay, sorry. Is some
Not
huh.
am I not audible?
Yeah, now you are audible.
Yes. So what is the question? This intersection now?
Hmm. So you are given two linked lists, L1 and L2, and you know that they intersect. So for example, L1 looks like this, L2 looks like this. Here is the position where they intersect for the first time. So you want to output this position.
Okay. So I keep on moving, and I keep on following the next pointer of the list L1 and the next pointer of the list L2, and at the point when I find that both the values are same, so that would be the intersection point.
Hmm. Okay. Uh, okay. So what you're saying is I will keep a pointer here, let's say um, P1, and I'll keep a pointer here at the start of this, and at every step we're going to move P1. So you're moving this simultaneously, is it?
So I keep on following the next pointer of the linked list L1,
But
and
if you keep on doing that, okay, in the next step P1 is here, P2 is here, then P1 is here and P2 is here. um, okay, and then when P1 is here, P2 is still here. Okay, so the intersection was supposed to be detected, but that did not happen. In the next step, P1 will move here and P2 will go here. So P2 is always lagging behind.
oh,
But if the number of nodes here, like before the intersection, if the number of nodes in L1 and the number of nodes in L2 is the same, then your algorithm works. Keep moving the pointers and you will find the intersection. So,
but then what if I execute, what if I traverse both the pointers independently? I mean, first I traverse the
hmm.
entire first list and then the second one, but then they will continue forever in that sense. But then still, I keep on keeping the track of the outputs, and whenever I find that
Hmm.
I found a point in which is common in both the traversals, so at that point I stop, and then
Hmm.
that can be done. I think if I do not execute, if I do not implement both the things parallelly and simultaneously, then this can be done.
Yeah, yeah. So, yeah, let me just write that. So, first idea was you keep pointers P1 and P2 for um, lists L1, L2 respectively, and increment P1, P2 um, by one step. If um, yeah, if P1 points to the same thing as P2, then output um, and output P1 and stop, else continue. But the issue was that size of L1 may not be equal to the size of L2. Okay, so we will come back to this um, but now for now let me write the second idea that was proposed. So you're saying that now what you do is you start with P1 um, as the start of the list L1, and P2 is the start of L2, and what you will do is, if um, yeah, so check if P1 is equal to P2. If yes, then stop. Else what you will do is P2 is equal to, else what you will do is P2 is equal to P2 dot next. Okay, and if this does not work out, then what you will do is P1 is equal to P1 dot next and initialize P2 to the start of L2. So okay, so basically what you're doing is keep your P1 here and just keep on moving P2. So compare P1 with P2, that doesn't match, move P2. Okay, so that doesn't match, then you move P2, compare P1 with P2, that doesn't match, move P2 again, this doesn't match, move P2, and this will happen till the end of it. Then in the next step what you do is you initialize P2 back to the start and move your P1 this time. So advance your P1 and make the same comparison. So with P1 here, check if it matches with any of the P2s. With that does not happen, then you keep P1 here um, and do a similar check. So what is the running time of this algorithm if we do this nested thing? Yeah, it will take order n square time. So this algorithm takes order n square time and does not require just order one space. Okay, so yeah, so that is there. Another way would be that if I were to allow you some space, if I let's say give you order n space, then what you could do is um, every time you if I were to give you some space, what you could do is create some copies. Okay, so just traverse through the list L1, traverse through this list. Whenever you visit a node in L1, we are going to mark it. So I'm going to mark it, mark all the nodes of the list L1. Okay, and then what you do is you traverse through the list of L2. So you keep on traversing until you see a marked copy. The first time when you see a marked copy, that's when you know that this is the intersection, because this was marked because it is in L1, right? So that is something you could do. If I give you order an amount of space, um, if I give you order and amount of space, then you can mark all elements of L1 in the first step. Okay, and second time traverse through L2, and if a marked element is found, then output that. Okay, so what is the time required for this algorithm? It's just order n, because you're just doing two simple scans. Okay, but let us say that I don't allow you that space. Okay, we don't have this luxury of space, you can't do these markings. Then what do you do now? We want to get this time down from n square to let's say I want order n time, and I don't want to use extra space. So if you create the hash functions, then you are still using some space, right? So for storing these mappings, you're still using some extra space. So I mean, let's say I only give you order one amount of space. So one hint is this itself. Think along these lines. So the previous idea was simple. It was that you keep moving the pointers, um, yeah, keep moving the pointers p1 and p2 one step at a time. But the issue was that um, these lists need not be of the same length. If the lists were of the same length, then the algorithm is completely correct. So there is a small observation you need to make, and then this idea will work as it is. Like it's a it has nothing to do with the data structures. The observation is just logic, as such, logic and yeah, some sort of combinatorics. That's all. Okay, so okay. So let us see. One thing that we assumed at the beginning is that the intersection is guaranteed. So this is L1. At some point, down the line, it is going to intersect with L2. Okay, so this intersection is bound to happen, and then this part is going to be the same. This part is going to be common to L1, and it's going to be common to L2. So let me say that there are n1 number of nodes here, and there are n2 number of nodes here. Okay, and okay, so but this part let us say that these number of nodes are L. Okay, so the number of nodes in L1 is equal to n1 plus L, and the number of nodes in L2 is going to be n2 plus L. Okay, so whenever the intersection happens, it happens at this point. So there is no point in looking at whatever lies before this, right? Just so let me split this n2 as n1 and n2 minus n1. Okay, so these these nodes don't even play a role. It's as if if I discard this point and then use the previous algorithm. If I discard this n2 minus n1 nodes and only look at this part, then that is same as your idea one. Keep a pointer here, keep a pointer here, and keep a pointer here, and now just keep moving one at a time. Just move pointer p1 and p2 one step ahead, and after n1 steps you're bound to find this position where they intersect. Okay, so the idea is that um, so how do I know how do I know how many
How
of
how many nodes to be discarded, man?
huh. So this the length of this is n1 plus l and the length of this is n1 plus l, so there are n2 minus n1 extra nodes here.
Okay.
Okay, so how do we find this? We um, find the number of nodes in L1. Let us say that is um, let us say that is m1, and find the number of nodes in L2. This is going to be and let us say this number is m2. How do we find this? Just scan through the entire list. This is going to take order n time. Okay, and now starting from L2, um, sweep through m2 minus m1 nodes. Okay, and that is how we are going to discard. So notice that this m2 minus m1 is nothing but n1 plus l. So this n1 plus l is m1 and n2 plus l is m2. So n2 plus l minus n1 plus l, which is nothing but n2 minus n1. Okay, so if you just find the total number of nodes here and total number of nodes here and you subtract that, you are discarding those extra nodes. And this is symmetric. It could be that L2 is the larger list and L1 is the larger list and L2 is the smaller list. Then we'll do the same thing appropriately. Okay, so those adjustments can be done. Okay, and now you, after this point, keep pointer p1 at start of L1 and pointer p2 at m2 minus m1 plus 1th node from L2, and now repeat idea 1. Then you do the same thing whatever we did earlier. Okay, and what is the time that we needed for this step? That was also order n. So altogether we are spending order n plus order n time, which is still order n, and we did not use any extra space. We just need some space to store the count m1 m2. That's all. So um, so this is our order n time algorithm. Um, yeah. Okay. So are there any questions about this? Okay. So let me modify the question slightly. Here we assume that there is an intersection. Let us say that um, you don't know whether there is an intersection, you just want to detect whether there is an intersection. Okay. So given two linked lists L1, L2, check whether they intersect. Um, so does the same algorithm work?
So what if there is no intersection then? Keep on traversing the list and till we reach to the end point and then we found that there is no intersection.
Yeah. So the same algorithm will actually tell you will just keep on traversing and reach the end of the list, and you will conclude that there is no intersection. Okay, so there is one comment here. What if L2 is inserted in the first root node of L2 intersects in the first root node of L1? Hmm. Okay, then if L1 intersects with the first node of L2, then they are essentially the same lists. Then their size is also going to be equal. Does that answer your question? But the same algorithm will work anyway. What it will do is um, yeah, find M1, find M2. These are going to be the same. M1 will be equal to M2. It will skip M2 minus M1, which is equal to 0 nodes. It will still remain at the start and execute the same algorithm. The first idea that we had. Just keep moving pointers. At the first step itself, you see a match and you say that there is an intersection. Okay. Okay.
So I have a general question here that which property of the memory
Hmm.
allows the creation of the linked list? Like say, the linked list is probably is not there in its natural form in Python, but this is very much used in C programming or in C++. Probably because there is a direct concept of using the pointers. So
Hmm.
my query here is that I can think of the some other data structures like wherein I maintain instead of maintaining two portions, I maintain say five portions. In the one portion, I maintain the data. Other portion, I maintain the next pointer, and then in the other portion, I maintain say the pointer to the 100 elements before. I mean this data point.
Hmm.
So which property of the memory allows the creation of the linked list and the handling of the linked list so very efficiently? And this is a natural, I mean, abstraction in some of the programming languages, and whereas some of the programming languages do not support it in its, I mean, original form. So why what is there under the hood?
Yeah, I may not have the answer to that question, but my understanding at a high level is just that um, you basically give access to the addresses, because of which you can basically point to it directly. And yeah, like you said, you can keep as many pointers as you want, or if you want 100 locations ahead or behind and so on, you can do that. But I don't know I don't know this in depth to yeah, at that, yeah.
Maybe something might be happening at the level of the memory, or how do we access the memory? I mean, how does processor access the memory? Maybe something related to that we do have access to the address of the next location and how this memory is organized. Maybe related to the architecture of the
Mm,
memory
yeah,
addressing scheme, etc.
yeah.
Yeah, yes, 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 right. Thanks. Yeah.
Okay, okay, yeah, sure. So, yeah, okay. The reason yeah, okay, I'll just come back to the question again. So, yeah, so we were asking, given two linked lists, can you detect whether there is an intersection? So, okay, so the reason I asked this explicitly is because while solving this problem, I came up with an idea which does not find the intersection, but it only detects the intersection. So I'll just yeah, I'll just state it. Um, yeah, if so, the thought is that you have okay, okay. Hmm. Mm, okay. So the thought was that given L1, what you do is reverse the linked list L1. This is something you can do in order and time. Um, this is something you saw in class. So let me just do that. Let me um, remove these pointers, and in the new list I'm going to reverse the directions. Okay, and also what I'll do is, this was the start of the starting of the list L1, so I will store that. So let us say that temp stores the start of the original start of L1. After reversing, this will be the new start, and this will be pointing to null, right? So I'm just storing this, the previous start. And now what you do is, you simply traverse through L2. Okay, so what will happen is, you start here, keep on moving, and the next pointer will take you here. But now that the arrows have been reversed, you will actually go back, right? You'll, instead of going this way, you will go here. This is the next position. You keep on traversing like this, and you end up here. This points to null. This is where you stop. And at this point, check if the final pointer is equal to 10, because if that happens, then you have essentially reached at the start of L1, and that means there was an intersection somewhere. Okay, so if this happens, if so, then there is a there is an intersection. um, Else output no. So this will not tell you where the intersection happened, because it just kept following the pointers. You don't know where the intersection was, but it just tells you that there is an intersection. So and this is also an order and time algorithm. Reversal takes place in order and time, the traversal takes place in order and time. So altogether, this is order and time, order one space algorithm. So yeah, I just thought of sharing this because I mean, yeah, yeah, okay, okay. Are there any questions about this problem, um, or like, yeah, about any of the two approaches? Good. So now, yeah, let's take a slightly. Okay. Okay. So, okay. So you're given a linked list L and you want to detect whether it has a cycle. You need not output the start of the cycle. That's fine. But yeah, okay. Even the detection itself is interesting. So how do we go about doing that? If the head pointer and the tail pointer uh, refers the same location. Mm, but the cycle could be intermediate, like it need not be like a cycle like this. It could be at some offset.
So if a node
Hmm?
if a node can be reached through the next pointer and the next to the next pointer. So
um,
like say this is not this explanation is not so like in this case what is happening that the node just after the loop can be reached to either through the next pointer or the next to the next pointer. Like say if you can assign some numbers to these nodes, then it would be easy for me to form the
okay,
argument.
yeah, so
Yes, so like the node number 4 can be reached is the next of the node number 3, and
hmm.
this is next to the next of the node 7.
Okay, you
So
can, if you were here, then in one step you can reach to 4. um, and you're saying from 7 with 2 steps we could have reached here.
yes,
Hmm.
so but then programmatically how to do this thing, because I keep on moving next, and then once I reach to 7, so how to ensure that this node has already been the next of this thing has already been visited. So we can do some kind of marking here, visited or non-visited kind of a thing.
Hmm. So if you allow the marking, then you don't need these 2 pointers as well. You just keep marking. Visit. So visit this node, and yeah, mark this, and so on. What will happen is eventually the node that you're trying to reach will already be marked, and at that point you know that there is a cycle. Right.
Yes.
But if I don't give you this marking access, then yeah. But this thought actually works, the one that you said. So it is kind of surprising. Um, and when I saw it first, I was also surprised by why such a simple thing should work. So the one step and two step that you were saying are what are called fast pointer and mm, okay, let me just check out this comment. So we pass two pointers at the same point if p1 is not equal to p2. uh, but where do you start p1 and p2? What are the starting locations? Okay, so you want to do like a nested thing. uh, Initially keep p1 and p2 at the same point, then move p2 by one step and so on. So this should be something like order n square time. uh, is that right? Is that what you are what you are saying? Yeah, that would be order n square. Why is it order n? If p1 and p2 start at the same position, then they will just keep moving together. Even if there does not exist a cycle, it will say there is a cycle. Is that clear? Like, I mean, let's say that this is a single linked list which does not have a cycle, and you keep your p1 and p2 here, and keep advancing them simultaneously. Then they will reach the end of the list, and you have concluded nothing um, about the cycle. Um, or even if there were a cycle, it will behave the same way. They will just keep moving together. Okay, so let me know at the end if yeah, if you want to discuss about this. So let me start with this idea. So the idea is that you keep two pointers. Okay, so one is a fast pointer, uh, the other is a slow pointer. So what the slow pointer does is that it um, uh, I I can't hear you if you are speaking. Okay, so what the slow pointer does is after every step, if it was pointing to p, it will point to the next. So p2 is going to be p2 dot next. But p1 is a fast pointer, so what it will do is it will be p1 dot um mm, okay uh, okay, so it moves two steps at a time. So for example, let us continue with this example. um, Initially p1 is here, mm, p1 is here, p2 is here. In the next step, um, p1 is going to move ahead by two steps. It's going to go next of next. So p1 will be here, and p2 only goes ahead by one step. It only goes to the next step. um, Now you check if p1 is equal to p2. They are not the same, but continue the process. p1 jumps ahead by two yeah, p1 jumps ahead by two steps. So p1 is here, P2 is here now. P2 is here. They don't match yet, but you continue the process. P1 goes ahead by 2 steps, so P1 is here and P2 is here. And now you repeat this. So in the next step, P2 will come here and P1 goes ahead by 2 steps. So P1 was here, it goes ahead by 2 steps. And now you see that at the next step they will match. P1 will jump 2 steps and move to 6. P2 will jump by 1 step and go to 6. So this is the point where they're going to match. Okay, so yeah, so the point is that okay, so before I explain this, is the algorithm is just that P1 moves, the pointer P1 moves ahead by 2 steps, pointer P2 moves ahead by 1 step, and the claim is that they're going to meet at the same position after some finite number of steps. So we're going to run this for k steps. I'll tell you what k is. Otherwise we don't want to run this infinitely, right? So run this for k steps. If P1 is equal to P2, then output that there is a cycle, else you output that there is no cycle, does not exist a cycle. Okay, so okay, right. So the question is, why should this work? What is the correctness reasoning for this? And
So what was the question? I could not hear.
yeah, why does this idea work? The fast pointer and the slow pointer thing. Like, how do you convince someone that if there is a cycle, then they must meet?
How do you decide the k value, man?
Yeah, we will. Yeah, this k will be answered when we answer the correctness. So if we can prove that this works, then that also will tell us what this k should be. So k will turn out to be order n, or even just 10 essentially. So actually this is just n. Okay, so okay, so let us see the correctness part. So okay, so let's say that we kept on doing this fast pointer and slow pointer movements. So what will happen is the fast pointer will keep skipping two positions at a time, and it will eventually reach this cycle. Okay, and it will keep on moving within this cycle. It will keep skipping 2 and it will stay in this cycle until the time p1 slowly comes and meets the cycle. So after some point of time, after basically after skipping um, these many points, p1 is inside the cycle and p2 is also inside the cycle. Okay, so so after skipping this chain, both p1 p2 are inside the cycle. And why is this important? Because once they are in the cycle, they will just keep moving inside the cycle, they are not gonna go back. So because all the pointers keep um, pointing within the cycle, so they are just going to stay there. So let us say that p1 is at this position and p2 is at some l steps, it is some l steps away. Okay, so this is guaranteed to happen. And now okay, and now what happens is, let's say p2 is equal to p1 plus l. What happens in the next step? In the next step, p1 moves ahead by 2 steps. So we are going to check if p1 plus l plus 2 is equal to p2 plus 1, right? So this moved by 2 steps, this moved by 1 step. We are checking whether these positions are meeting. If that does not happen, then we are going to check if p1 plus p2 plus 2 in the next step, are they going to meet, right? And you keep on doing this, you keep moving 2 steps at a time and keep moving 1 step at a time. But notice that this is not exactly equality, everything is modulo the length of the cycle, right? So so let me do that. So this is actually congruent modulo k, where say k is the length of the cycle and this is at most n, because the number of nodes itself is n, so the length of the cycle is at most n. And so this is essentially what we are checking. Okay, and now observe that if you sorry, this is p1, right? p1, yeah, this is p2. Okay, right. So observe that so this p1 and p1 just cancels off, and observe that there is a value of l for which this this inequality will always be satisfied. So I mean, for any value of, for a fixed value of k and for a fixed value of l, this uh, this equality will always be satisfied. So l plus 2i is congruent to I mod k always has a solution for fixed k comma l. So that's the yeah, that's a simple reason why this works. Okay, so basically we are just writing whatever is happening within this cycle, we are just writing it down in terms of, in mathematical terms. And yeah, that just tells you why this logic works at all. And yeah, and this algorithm is due to Floyd. So this is Floyd's algorithm originally. It's also called fast and slow pointer algorithm. So yeah, so that's it. The algorithm is simple. The correctness part was just observing the combinatorics.
So can this ever happen that both P1 and P2 points to the same node within the cycle?
Yeah, that's what we are claiming, right? At the end, this, I mean, at the end, P1 will meet with P2.
P1 will meet with P2 is fine,
Hmm.
but inside the cycle, say if we iterate one more time, and if both P1 and P2 are at the same location,
Hmm.
then this, I mean, they will never meet second time.
Oh, so once they've met, will they meet again? Is that
Yes, yes, yes.
they should meet again at the same point? Or mm,
Because then P1 will move one step ahead, and P2 will move two steps ahead.
hmm. Mm, yeah, that seems. Yeah, that seems correct. Hmm. Yeah, I think even in this equation, if you put um, if P1 and P2 are at the same position, then this L is 0, right? The offset is 0. So yeah, so you want I to be equal to 0 mod k. If L is 0, then you want I to be equal to 0 mod k, which means okay, so after k steps they should meet. Okay. So if they're already here, you repeat this process for the length of cycle many times, which is 5 in this case. After 5 steps they should meet.
Right, if there is a loop.
Hmm.
Correct. Fine. Thanks.
Okay. Mm, yeah, any other questions? Okay. So I'll move on to the next question. This should be, yeah, this is simpler than the previous two. So you should, yeah, you'll get this quickly. So question is, I'm given linked list. Okay. Given linked list, sorry, check if it is a palindrome. Okay, so for example, I have yeah, for example, this is the linked list that I have. Then the values written here form a palindrome. So I want to output that. Yes, it is a palindrome. Otherwise, if this were some other letter, I mean, if it does not, then say no. Yeah, if this were a doubly linked list, if you had pointers in both the directions, if you had the reverse pointers as well, then this is very easy because you will.
Sorry, man.
Mm,
Can you please tell about the palindrome, please? What is
yeah,
palindrome?
yeah. So, um, any word of the form WW reversal. Okay. Um, yeah. Um, Okay, so basically palindrome is something that if you read from left to right or right to left, it's the same thing. So if I were to read this
Yeah,
from
thank
here,
you, thank
yeah.
you. Yeah,
So
yeah, got it, man.
basically
Thank you.
W is W reversal. Okay. Yeah, so there is one suggestion in the comments which says that I'll keep two pointers. I'll keep first pointer here, and the second pointer I'll keep traversing and um, go to the end. And maybe the idea is that you keep moving p1 to the right and keep moving p2 to the left and keep comparing. Check if a is equal to a, then move one here, move the other here, check if the contents match, move both again and check if the contents match until you are at the same position. But this would work if it were a doubly linked list, because in a doubly linked list you have access from this node back to the previous node, whereas in the singly linked list you can't go back from here to here. The pointers are all pointing only in one direction. So p1 is possible, moving p1 is possible, but p2 is not. But what you could do is, let us say you want to simulate this idea, right? You want the reversals to be there. So on this side, you want pointers to um, point to the left, whereas from this side, you want the pointers to So how do you achieve this? How do you, so essentially you are saying that go to the middle element. Let us say this is the middle element. From this point I want to reverse this array. I don't want these pointers, but I want these pointers. Isn't it? So what is the algorithm? Scan through L, find the number of elements in L. Let us say this is equal to n. Then let mid be equal to n by 2, ceiling or whatever. Okay. And then what you do is you reverse the array, reverse the list from mid plus 1 to starting from mid plus 1. So what will happen is the list will look like this. The first part remains the same, but from this point we have reversed the pointers, and now we will do whatever you said. We will keep one pointer here, keep one pointer here, keep one pointer here, and keep moving. Check if p1 and p2 have the same content. Yes, then keep moving ahead. Now you can go from here to here because the array is reversed. You check this again, and finally you will meet in the middle. And at every position, check if p1 and p2 are the same. Okay, so how much time does this reversal take? So this step takes order and time. We are finding the number of elements. How much time does the reversal take?
Order n, ma'am.
Yes, so that is also order n. Okay, so overall your and after this point we are just um, keep pointer 1 at the start of the list and pointer 2 at the end, and keep moving. Okay, check if ptr1 is equal to pointer 2. If no, then you already know that it is not a palindrome. Else check if ptr dot next is equal to pointer 2 dot next, um, and stop when okay. So that's the entire algorithm. Okay. Okay. Are there any questions about anything so far? Mm, okay. Okay. So next, yeah, we'll talk about this abstract data structure called stack, which was introduced in the lectures. So what does the stack do? Stack supports the following It operations. It okay. There may be other operations that you can add and so on, but the basic operations that we want the stack to support is what is called push an element, and pop. So what does that mean? Um, so think of this as storage. Initially this is empty, and I want to push an element here. So suppose I want to push the element 1, then 1 is now at the top of the stack. Now let's say I want to insert one more element. So insert, or so what we did first is we did push 1. Now I want to insert another element. Let's say I want to insert 2. So what will happen is 2 will come at the top of this, and let's say I do one more push, so 3 comes at the top of this. And at any point of time you can only access the element at the top. You don't know what is below. All you can see is what is at the top. Okay, so if I want to remove some elements now, that's the pop operation. What pop does is it removes the top element. So now if I do pop, okay, then 3 goes away. So 3 is no longer there, and now 2 comes at the top of the stack. So if I were to access the stack now, then then 2 is the only element I can see. If I push few more elements, if I do push 4, push 5, then this is what it would do. Okay, so these are the two basic operations that we wanted to support. Okay, so how do you implement this? I want to implement this data structure using a linked list. So each node contains the data that we wanted here. It's some value, and it has a pointer. This is how every node looks like. So 2 looks like this, and so on. Okay, so we want to implement stack using linked list, and I want the push and pop operations to be efficient. I want them to be order one operations. So how do we do this? Hmm. Okay, yeah. So you simply think of yeah. So let us say, so what I'll do is I'll make my linked list as follows. If I want to push one, I'll create a node like this. Now this operation is done in order one. I want to push two. So what I'll do is I'll create a node called two, and make this the start of my linked list. I'll insert it at the first position. Okay, so um, so if you, I mean, this is basically the same view as this, but I'm just rotating it sort of. Yeah, so that happens in order one. Now you want to push three, so you create this new element, make it the start of the linked list, and make it point to this. So then you have two, then you have, yeah, then you have two, then you have one, which points to nothing, and this is the start of your list. Now this is also done in order one, because all you did was created a node and made it point to the start of the list. Now when you have to pop this element, all you do is delete this element and make this the start of your list, and the subsequent push operations are similar. So here push is nothing but insert element at the start of the list, and this can be done in order one time. And pop is nothing but delete the first element in the list, and this also can be done in order one time. So this is a linked list, gives you a very efficient way of um, um, I mean, implementing the data structure uh, stack. Okay, so similar to stack, there's another data structure called queue, as some of you have mentioned in the chat as well. Um, so this borrows the same intuition from real life queues. um, yeah, if there is a queue of people somewhere, then let's say this is the start of the queue, the new person coming in should uh, should go to the last position, which is vacant, and the first position standing in the queue should be the one that's processed first. And this is how the requests and processes should be managed as well. So it has a very natural reasoning. So what that means is, whenever you do insert, you want to insert at end, and whenever you do a delete, you want to delete from front. Whereas in case of stack, you wanted to insert at front and delete from front. So this operation is called dequeue, and this operation is called enqueue. Okay, so yeah, so let us say that I want to implement this using linked list. I want both these operations to be um, fast. So Okay, so let's okay, so let us say that I make the same linked list. Okay, this is my linked list. Assume that this is in some order. Now let us say I want to delete, I want to dequeue. Where should I dequeue it from? I should dequeue it from the beginning. So what I'll do is I will, when you say dequeue, I will remove the first element and make this as the new head pointer. So this is an order one operation. This is fine. This is fine. But now I want to perform an enqueue operation. That means I should insert it at the end, right? So in order to insert this new element here, let us say this is the new element. In order to do that, I will first have to traverse the list all the way to the end, create this new node, and make the last node point to the new node. So this is an order and time operation. This is an order and time operation because we need to access the last node, right? So this will incur us some cost. We need to go all the way to the end. But I want, if I'm dealing with this data structure and these are the two operations that I care about, then I want both of them to be fast. So um, so how do I modify this list? Let's say I keep some extra pointers and so on. How do I modify this to um, yeah, yeah, exactly, you will maintain a doubly ended um, yeah, doubly ended queue. So what you could do is keep pointers both ways, and now you could either do the following: keep a pointer, maintain a pointer to the start and maintain a pointer to the end, so that whenever a new element comes you will add here, you will delete from here, and whenever you want to add you will um, create pointers like this. Or what you could do is, if you don't want to maintain the two pointers, you make it circular. So if this is some nth element that was added now, then you make it point to the first element. And this is the only thing we will remember. Whenever I want to delete, I will delete from here and make this. Okay, so let us say I want to delete or dequeue1. Then what I'll do is I'll keep the rest of the list as it is, delete one, and make these two pointers point to each other, make this the head. And if I were to enqueue let's say n plus 1 into the list, then what I do is keep the rest of the list as it is, insert this new element. How do I okay, and um, yeah, use this pointer to access n. Okay, now that you are at n, you edit this edit these two edges, and you already have the head pointer, so you can always edit these two edges. So this two-way access will make sure that from one you can always come back to the last element. That's it. So you don't need to make keep two pointers, or else if you don't want it to be circular, you can as well keep two pointers. Okay, so now enqueue is also an order one operation. Okay. Okay, good. Um, okay, so now we will move on to the second theme that was discussed in the classes, which is called the binary search trees. Okay, so so how did we define the binary search trees? These are binary trees with the property that the value at a node n is at least the value at um, the right of the node, and it is at most the value at the left of the node. This is true for all nodes, n dot left. So for example, if I look at this tree, everything here should be a smaller value and everything here should be um, a larger value. Okay. Okay, so this should be, let's say this is 50, this is 100, and then to the left of 50 you should have something smaller than 50. Let's say 45, and then you have 60, yeah, and so on. It may not be a complete tree, but it just respects the property that for a node everything to its left is smaller, is at most its value, and everything to the right is at least its value. So natural reason why, I mean, why such trees are defined in the first place is because it makes search easy for you. For example, if I have to okay, I'll just make this example slightly. Okay, yeah, so for example, if I have to search for 48 now, what you will do is you start here, check if this number is 48. If it is not, this is similar to your binary search algorithm. If this number is larger than 48, then 48 can only be here, it cannot be to the right of the tree. So this entire search is halved, almost halved, it's not exactly halved. If it's okay, so now you go to 50 and repeat the same process. Check if 48 is equal to 50. If it's still larger, so you go to the left branch again, and so on. Okay, if it was smaller, then you go to the right. Have exactly the same intuition as binary search trees. So um, idea is motivated by binary search. Okay, and why do we do this? Because we want the search to be fast. We want search to be fast. Okay, so if the height of this tree is h, height is the largest length of a path from root to leaves. So if h is the height of the tree, then what is the insert time? Insert, delete. Okay, delete is slightly complicated. Let's just talk about search and insert.
What is the question, man?
So if h is the height of the tree, the binary search tree, then what is the time required for insertion and search?
Log n time?
Yeah, h is the height, so if h is log n, yeah, then it takes log n time. So this is h. Now yeah, I think, yeah, all of you are probably familiar with the fact that if a tree is full, in the sense that every node has almost two children, then the height of a tree with n nodes is log n. So if t is full, then um, height of tree is order log n, where n is the number of nodes in T. Right. So that means if I want h to be smaller ideally. So if n is the number of nodes and if the tree is nicely balanced, then the height of the tree is logarithmic, which is very nice because that makes the search fast, that makes insertion fast, and eventually it makes deletion also fast. Right. So that is the idea. But it could be that in the process of making of inserting, we ended up increasing the height of the tree by a lot. So one worst example that's you would have already seen is, let's say that insertions come in ascending order. So you have this tree, yeah, you have one, then you want to insert two, so two should go to the right of this, then three comes, three should go to the right of this, and so on, all the way up to n. So this is a binary search tree, but because the insertions came in this order, the height of the tree is order n. This is really bad for us because every time we want to insert, we have to walk all the way down, right? So that means we want to maintain some sort of a balancedness is needed, um, because we want h, the height h to be small. When we say small, we mean something like order log n. Okay, so something needs to be done in order to make sure that the balancedness property is restored. So yeah, I think okay, I'll not talk about the balancedness right now, but I hope the idea of balance, the binary search trees itself is clear. So let me just do some we'll do some exercises. So okay, let's do a simple thing and let's just take this a random set of okay, so let us say I want to insert in this order. So let's just make the tree for now. Okay, so first I have 60, now I want to insert 25. So where should 25 go?
Left.
Yeah, to the left of this. Then I want to insert 7. Yeah, to the left. I want to insert 2. That also goes to the left. What about 15?
Make
So
up 25.
15 will become the right of 7.
Yeah, it will become the right of 7, because 15 was smaller, so you move to the left. 15 was smaller than 25, so you move to the left. But now 15 is larger than 7, so you go to the right. What about 30?
Right of 25.
Yeah, it will go to the right of 25. Then 68.
Right of 60.
Right of 60.
Yes, right of 60. 101.
Right of 68.
Yes. 13. To the left of 15. Yeah, so 13 goes here. 18.
Right of 15.
Yeah, 18 goes to the right of 15. And finally 47.
47.
Right of 30.
Yeah, it goes to the right of 30. Yes. So yeah. Okay, so in this case, what happened was that, if you look at the height of this right subtree, there were very few additions that happened here. So this is very sparse, but on the left side it's very bulky. It has a larger height, it has larger number of nodes as well. So um, so the balancedness itself can be defined in several ways. For example, if I want height to be balanced, so there are different notions of balancedness. Um, okay, so for example, I could want the height to be balanced. In that case, this is something you have seen in the class. You want that for every node, x, you want that um, the height of tree subrooted at okay, how do I mm, okay, let me write it this way. Okay, so T of L denotes the left subtree of x, and T of R denotes the right subtree of x. So for every node we want that um, the height of the tree rooted to the left versus the height of the tree rooted at the right, they are almost balanced. Either ideally they are equal, if not they are at most one. There's a difference of at most one. That is one notion. So for example, here the height of the on the largest height on the right side is this path, which is 1 2 3 4 5. So this is of length 5. Height of left subtree is 4, and here you have, if you look at the right subtree, the height of the right subtree is just 1. So there is a disbalance here. This constraint is violated. Another notion of balancedness that one could think about is in terms of number of nodes, or it's also called weight balancedness, also called weight balancedness. I don't want, so here on the left subtree, how many nodes are there? 7 8. You have 8 nodes here, you have only 2 nodes here. So in some sense the weight of the subtrees is imbalanced. So in some situations you may want to keep your I mean, the problem itself requires you to have such kind of balancedness so that the operations are faster. So this is another well studied notion, and you can come up with like design more and more notions, but this is the more generally um, I mean yeah, I mean, generally studied notions. You would have probably seen AVL trees in the class.
Madam, left subtree height is 3 or 4?
Left
Left
subtree
subtree
height
height.
is yeah, left subtree height is 3. Yeah, thanks. So this is 3. Okay, thanks. um okay, so okay, so that's yeah, that's all I'll say about this. um okay, maybe this is coming up in the lectures. I'm not entirely sure to what extent this will be covered, so I'll just start off with okay. Okay, this is something that some of you might have seen, but let me just ask it anyway. So mm, let us say you are given a BST. um, Converted to a sorted array in in order in time.
If we do in order time traversing, I think that will be get sorted.
Yeah, that's correct. So if you do an in order traversal, that is you go to the left, then you visit the node, then you go to the right and keep on exploring in this fashion. Then yeah, so let us just do that maybe for this example. So let us start the exploration from this point. It says you go to the left, so that's the rule. You go to the left. So now you are here. At this point again you go to the left until you can't. At this point there's nothing to the left, so you are going to visit this node. So you get 2, and once you are done visiting you'll go to the right, but there's nothing to the right, so you come back and you're done exploring this node. So so you come back. With respect to this node, you're done visiting the left part, so you're going to visit it 7 and go to the right and continue this recursively in the similar manner. So 15 will take you first to 13, you will end up visiting 13, go back to 15, and so on, go to 18. So observe that this does indeed give you yeah, the sorted order of arrays. Okay. I'll go later. I'll go later. Okay. Okay. So I mean, there is a way to prove this. The proof is by, you can prove this inductively. Okay, so why does this work? Because before you visit a node, you make sure that everything to its left was visited, and and only after you visit this node, everything to the right is going to be visited. So for every node, n, before we write n, all the values smaller than n appear here are to the left, and all the larger values all values larger than n are to the right, and this holds inductively for every node. So therefore by induction, this is the proof that it must be sorted. Yeah. Okay. Mm, okay. So okay. So I'll just write a question. Maybe we'll not have. We'll take it up next time, but or okay, we may not. But I'll just write this as an exercise. Um, if you're familiar with the AVL balancing, um, or the balanced binary trees in that sense, so or the balanced binary trees, then yeah, then the worst case example that we had was for the binary search trees was that the elements come in the sorted order. If I were to insert one second. So, if I were to insert elements in the sorted order, then the worst case example for um, binary search trees was that you ended up with just a long chain of high 10, right? But how does this balancing help? So there are these left, right, and so on rotations, the 4 kinds of rotations that you do. So it is an interesting exercise um, to keep inserting elements in the sorted order, and yeah, and see how this balancing works. So okay, so I will yeah, I'll have to cut the tutorial slightly shorter right now. But are there any questions about are there any questions about whatever we discussed today? um,
So, which topics shall we cover next time?
what is the weak contents? I haven't seen any idea.
Okay,
Okay, yeah,
week 6.
yeah. Okay, the next tutorial is again on Tuesday, same time, 7 p.m. to 9 p.m. Okay. Okay, so okay, see you all next time.
Thank you. Thank you very much.
Thank you.
Thank you.
Thank you so much.
Thank you.
Thank you.